Let's jump right in. We usually operate under a pretty simple, logical belief, right? The idea that the more safety rules, procedures, and backup systems we add to a complex process, the safer it's going to be. The goal is to just engineer human error right out of the equation. But reality actually contradicts this almost immediately. Take VoluJet Flight 592 back in 1996, a tragedy with 110 casualties. But here's the thing. That disaster didn't happen because they lacked safety regulations. Actually, it was the exact opposite.
When investigators dug into how the airline was maintaining its MD-80 aircraft, they found that all the safety procedures were completely correct by the book. The problem? The maintenance manual itself had become this massive, bloated document. It was so layered with regulatory additions and complex cross-checks that it was practically unreadable. It wasn't ignored because people were lazy or malicious. It was bypassed out of sheer necessity just to get the job done. And this consequence points us toward a hidden structural force. A force where the very things we build to guarantee safety actually become the invisible hazards that guarantee failure. Let's look at how this happens in this explainer.
Section 1. The paradox of safety. When eradicating error escalates risk. We need to explore a deeply unsettling structural paradox. Our relentless attempts to eliminate human variability and error do not actually eliminate risk. Instead, they transform it, leading to unintended and escalating outcomes that we cannot foresee.
So here's the core contradiction we're dealing with. We do the rational thing, right? We bolt on more procedures, add automated checks, stack up safety layers, all to achieve this perfect, unyielding reliability. But as those layers pile up, the inner workings of the system start to get murky. They become completely opaque. The true state of the system is suddenly invisible to the very humans who are supposed to be managing it. Basically, we end up trading visible, local errors for invisible systemic vulnerabilities. To really see how this structural shift happens, let's establish a baseline physical system. Picture an early, purely mechanical aircraft. You've got a pilot in the cockpit, hand resting on a throttle lever. Connected to that lever is a simple, physical steel cable running straight to a valve on the engine. The pilot pulls the lever, the cable moves, the valve opens. It's direct, it's observable. If that cable snaps, the pilot instantly feels the loss of tension in their hand. The whole setup is entirely transparent.
Section 2. The illusion of control. Escalating technological interventions. Because human hands can be unsteady and our minds get distracted, engineers naturally seek to control this variability through technological intervention. Notice how our physical system begins to evolve. Safety engineers decide, hey, the pilot shouldn't be able to push the engine past safe limits. To fix this, they drop a digital sensor right into the linkage between the lever and the valve. This sensor constantly monitors the input and can literally override the pilot's physical action to prevent a local mistake. Suddenly, we've introduced a layer of interpretation between the human and the machine.
And look, we have to acknowledge that this approach makes total sense. Consider the number 5. That represents a 5-fold increase in global aviation safety since the 1980s. Which is exactly when we started heavily transitioning to these automated sensor-driven systems. Because of this massive success, going backwards, returning to the era of purely mechanical cables and raw human control, is statistically impossible and, frankly, totally undesirable. We are locked onto this path of automation.
But this rational progression creates a really disturbing new behavior. What's it doing now? That is actually one of the most common questions you'll hear in a modern, highly automated cockpit. It's a phenomenon known as automation surprise. Pilots have basically been relegated from active flyers to system managers, and they find themselves just watching these incredibly complex flight guidance systems switch operating modes entirely on their own, reacting to sensory inputs that the pilot can't even see or verify. The system acts independently, and we allow this contradiction to exist. The machine is deemed safe, yet the operator sitting right there has no idea what it's actually doing.
Section 3. Invisible chains of interaction, merging vulnerabilities. Here, we'll see how isolated, highly rational fixes begin to silently merge. As we add more layers to prevent isolated errors, we inadvertently create invisible chains of interaction.
Think about how this complexity plays out on the ground. We build in redundant backup systems to ensure safety, right? But maintaining all these overlapping systems takes a massive amount of resources. So workarounds naturally emerge. You've got overworked maintenance crews dealing with strict time constraints and huge pressure to keep operations moving. Rationally, they might defer maintenance on a tertiary backup system. It's a local optimization. They know the primary system is going to hold. But they are making decisions about components whose hidden interactions with other, dormant layers in the system are literally impossible to fully map out.
Let's update our physical system again to see this extreme escalation.
That steel cable, it is completely gone. Now, when the pilot moves the lever, they are essentially just sending a digital request. Between their hand and that engine valve sit 3 redundant computers, running millions of lines of code, constantly cross-checking atmospheric sensors and talking to automated flight management systems. The pilot's hands are entirely off the physical controls. The architecture isn't mechanical anymore. It is purely computational, and it is deeply, irreversibly opaque.
And here is where we can finally name the mechanism that's been silently driving all of this. This is Charles Perrow's concept of the system accident, sometimes called a normal accident. When you have an architecture characterized by high interactive complexity and tight coupling, meaning processes happen so incredibly fast that they can't be isolated, multiple minor, seemingly unrelated failures are inevitably going to interact in ways nobody anticipated. The structure itself is so dense that a catastrophic failure isn't some freak occurrence, it is a normal, entirely inevitable output of the architecture.
Section 4. The trap of past success, the inability to reverse course. If we know this tightly coupled architecture is inherently vulnerable to system accidents, why can't we simply engineer our way out of it? Why don't we just simplify? To understand why, look at historical infrastructure. The standard railway gauge used across more than half the world is exactly 143.5 centimeters. Engineers have known for a long time that wider gauges give you better performance, higher speeds, and way more stability, but we don't use them. Why? Because that specific 143.5 centimeter width was copied directly from primitive coal tramways in early 19th century Britain. That totally arbitrary historical accident trapped the entire globe in an inefficient architecture simply because changing the standard later on became physically and economically impossible.
If we jump back to our aviation system, we see the exact same trap. Think about those millions of lines of code in the flight computers. A lot of that code actually governs automated safety layers that aren't even actively used anymore. But it stays there. Why? Because the regulatory certification required to prove that deleting that code won't cause some new, unexpected failure is just too expensive and complex. So this dormant legacy code just lurks there, completely unseen in the flight management systems, adding all this invisible mass to the system's overall complexity.
We've hit our second structural constraint here, path dependence. Early design choices, whether we're talking about the width of a 19th century coal cart or the installation of an early safety sensor, create an irreversible lock-in. The legacy of our past successes and our past safety fixes completely dictates our future vulnerabilities. We can't just start over from scratch. We are forced to build on top of a foundation that is getting increasingly brittle.
Section 5. Irreversible structural lock-in. Brittle versus resilient architecture. We need to contrast the brittle architecture of our engineered systems with the natural resilience we see in biology.
Let's consider an analogy from safety researcher Richard Cook regarding human bone. Bone is incredibly resilient, but it doesn't get that way by avoiding stress. Actually, bone requires mechanical strain, friction, and even microdamage to trigger the biological processes that keep it strong. It literally uses stress and uncertainty to maintain this dynamic, continuous balance of creation and destruction. If you take away the strain, the bone just wastes away.
Now, contrast that living resilience, what researchers call graceful extensibility, with our engineered networks. Living systems adapt by being exposed to variability, but our automated systems are designed to entirely eradicate all stress, all friction, and any trace of human variability. By trying to isolate the system from every conceivable minor shock through these rigid, stacked layers of automation, the architecture loses its ability to flex. It becomes perfectly robust against the errors we already know about, but fundamentally brittle the second it faces something unknown.
Let's take our physical system track to its final conclusion. An atmospheric sensor feeds an anomaly into the first computer. The second computer interprets that anomaly as a critical fault and instantly initiates a safety protocol. But that dormant legacy code we talked about, it conflicts with the protocol. Suddenly, the redundant systems are completely deadlocked. Screens start flashing conflicting data to the pilot, sensors freeze entirely, the human operator is left completely and physically disconnected, just staring at opaque screens, totally unable to reach through the void to manually turn that engine valve.
And this leaves us with our final, crucial realization. When these massive, complex architectures cascade into disaster, it is not because a single component broke, or a person failed, or some rule was ignored. It is because the tightly coupled, path-dependent layers interacted flawlessly. Complex disasters are not a breakdown of order. They are the rational, inevitable fulfillment of the system's very own architecture. The system wasn't failing, it was simply following its structure to the very end.
So, the next time a massive technological failure dominates the news, you really have to ask yourself, was it truly an accident or was it a guarantee?